exact room on this exact topic. So it's a little bit weird, a feeling of déjà vu, because this might be one of my last talks on this subject. I've done other things in between, but at least with this particular point of view, because things have now finally sort of come to a reasonably nice conclusion, and this is what I'd like to tell you about today. So the talk is based on several joint works with Julien Bichon, with Sven Raum, Stefaan Vaes, and his student Matthias Valvekens, but I will give credit where credit is due when we get to the research part of it. I decided to give a Blackboard talk because Blackboard talks are easy to change. I didn't really know which audience to expect, so I suggest that you just interrupt me whenever you feel like it, and I will adjust the talk accordingly. But as you can see, it's a little bit of an off-topic thing. First and foremost, because subfactors do not enter at all into the title. So I think I would like to start off talking a little bit about groups, something that you're most likely all comfortable with. And groups here will be discrete groups. So you may think of it like a free group of generators, SL3Z, the integers, something like that. You could also think of a finite group, but things will be a little bit trivial or degenerate in the case of a finite group, so let's stick to an infinite group. And I'll call it gamma throughout the talk, so this will be a group, and my discrete groups will always be countable. I don't want to deal with something like the reals considered with a discrete topology. And when you study groups, as in many other mathematical fields, you have a cohomology theory. So let's say that my group acts on X, which is a vector space. And then you can associate to this situation the group cohomology of gamma with coefficients in this vector space. And there is one for each positive integer p. And if you're not familiar with it, let me just stick to the case p equal 1 throughout the talk, because there you have a very hands-on description. So if p is equal to 1, then I need to describe what the first group cohomology is. So I need to tell you what the co-cycles are and what the co-boundaries are, and then of course the cohomology is the quotient of the two. So I need to define what I mean by Z1 gamma x. And these are just the maps from the group to X itself that satisfy the cocycle relation. So gamma mu, if I put a product of two elements in there, I get the following. I get gamma acting on C of mu, and then plus C of gamma. Okay, so this is just the definition. This is the relation that a cocycle needs to satisfy. And there's always a trivial source of such cocycles, namely the coboundaries. And I get a coboundary by picking a vector in X, and then I look at the map, which just sends the group element of xi minus xi. So it just shifts and subtracts. And it's a one-line computation to check that such maps will always satisfy the cocycle relation. There is one for each element in the module X, and the one cohomology is then of course just Z1 divided by B1, measuring the extent to which this module X allows for non-trivial cocycles. Okay, and there are higher cohomologies, H2, H3, H4, etc. And these are interesting for many reasons, and they tell you a lot about the group in question. If you are more operator algebraically inclined, you will realize that this is something you know quite well. It's the Hochschild cohomology, you see, of the group algebra with values in the bimodule X. However, I have not told you the bimodule structure on X yet. So what do I mean? Well, if I have my group, I can always associate to it just the linear span of the group elements. So this is just a formal vector space with basis the group elements, and this, it turns out, is a star algebra. Because I can add things because I'm in a vector space, and I can multiply things because the group law gives me a way of multiplying, and the inverse gives me a way of forming stars. So this is a nice unitary algebra, and as soon as gamma acts somewhere on X, C gamma also acts because I just extend linearly. So I get, every time I have a module for gamma, I get a module for this ring in the homological algebra sense. So I can pass from gamma on X to C gamma on X. So now I have one action, and the other one I just get by acting trivially on the right of the module. So I have the designated trivial representation, which just takes any group element and sends it to 1. And this extends to a ring homomorphism, also here. And I can then consider X as a bimodule with this right action. Now I have a ring, and I have a bimodule, and it's easy to check that this relation exactly means that C is a derivation into the bimodule, so it satisfies the derivation property, and the innerness is exactly the innerness of the derivation. So if you don't like to think about groups and group cohomology, but like to think about algebras and algebra cohomology, I don't know whether you do that, but this is at least an option. This is just the ordinary Hochschild cohomology with values in this admittedly slightly trivial bimodule because I have just added an artificial trivial right action to it. Anyway, what I'm going to be particularly interested in is the case where X is just the L2 space of gamma, so the square summable sequences, and gamma just acts by translation. And what I'd like to know is what is HP in general, say, gamma L2 gamma. And on the surface of things, this is a horrible idea, because this, in general, has a tendency to be either 0 or infinite dimensional as a vector space, which means that it really captures very little useful information about the group itself. So I'm not going to bore you with looking at this as a vector space, but I'm going to rather look at it as a module over the group von Neumann algebra and assign the so-called von Neumann dimension to it, which will lead to a non-trivial invariant, something which is not as often 0 and certainly not infinite dimensional. So the idea is to look at, and I'm going to define this, not the linear dimension, but the dimension relative to a von Neumann algebra of this guy, gamma L2 of gamma, and this is then what's called the L2 Bethe numbers of the group gamma. So if you know what this L gamma dimension means, fine, then you know what all these beta p's are. If you don't, again, I'm going to only say something about it when p is equal to 1, but this is already an interesting case which captures a lot of information about the group and its analytical properties. So I'm going to assume now that p is 1, and I'm also going to make a small technical assumption that is probably not going to annoy you too much. It's just that the group is finitely generated. Because if the group is finitely generated, you can get a more hands-on description of it. So I'm going to assume that gamma is finitely generated by, say, gamma 1 to gamma n. And then I want to describe what this dimension thing is. And why do I want the finite generation? Well, I want it because in that case, I get a handle on the cocycles. Because very much like a homomorphism out of a finitely generated group is uniquely determined on the generators, so is a cocycle, right? Because if I know it on a done generators, I certainly know done products of generators and iterated products of generators and so on. And you can also get the inverses. So everything there is to know about the co-cycle here is determined on its values on generators. So what I get is a map to an n-fold copy of this Hilbert space, which simply takes gamma 1 up to gamma n and stick it into the co-cycle. This is an injection. Fine. So I haven't done much. I've just taken one vector space and stuck it into another vector space. But I do gain a little bit more information because this is not an arbitrary subspace. Actually, it turns out that so this is first and foremost a closed subspace in there, which means that I can look at the projection onto it. So this is a closed subspace. So I get a projection P onto it. And because of the co-cycle property, it's easy to check that if I act with the von Neumann algebra diagonally on the right, this is stable under the diagonal right action. So another way of saying this is just that if you sit down and check this P is actually just an n by n matrix over the group von Neumann algebra. You all comfortable with group von Neumann algebras? Yeah. So it's not only a matrix of bounded operators. Each and every entry is actually in this guy. And this is very useful because then I can just define the gamma dimension of the co-cycle space as the diagonal trace of this guy. So what I mean here is just the natural trace on gamma that just is given by the drag element at the identity. So what is this? Well, it's a number, but at least it has the decency to be at most n, right? Because it's the diagonal trace of an n by n projection matrix. So I wanted to not measure the co-cycle space. I wanted to measure the dimension of the cohomology space. So if you take instead your co-boundaries and embed them via this map, I didn't give it a name, iota, then you get a space. It's not necessarily closed, but if you close it off, you get something which is one-dimensional in this sense. Okay? So it's reasonable to define the first L2 number at least of gamma as this dimension over the Z1 space minus 1. Okay. So this
it does not depend on the generators.
It does not depend on the generators. It does not. It's intrinsically a property of the group, and you can actually. So you can develop a whole algebraic notion of von Neumann dimension where any algebraic module has a dimension, and then of course this as a module for this has this dimension. So I'm trying to bypass a lot of algebraic machinery and just give you a sort of hands-on working definition of beta 1 that you can use throughout the talk. But it is completely independent on the choice of generators. So you can do something similar in particular for higher P's, so you get a whole sequence of numbers here. And as I said, it's clear from at least that picture that when the group is finitely generated, at least, these will not be infinite. So it's at least a non-infinite dimension in certain, in many interesting cases. So the question, of course, is what do these tell us? What kind of information is contained in these L2 numbers? And in contrast to other Betty numbers, ordinary Betty numbers, they do have a great tendency to vanish. So let me give you a couple of couple of computational results. So first and foremost, it's so that if gamma is amenable, then all these L2 numbers are just zero. So they don't distinguish anything within the relatively large class of amenable groups. This is the result from 86 by Kyed and Raum. So you might start wondering whether they see anything at all, but they do. They do see free groups, for instance. So beta P2 of a free group on n generators is just n minus 1 when p is 1 and 0 otherwise. And you can somehow feel this, right? If you look at the definition up there, if I have a free group on n generators, any assignment of a vector over there will extend to a cocycle because of the freeness. So I can just map the generators to an arbitrary choice, which means that this iota over there is actually surjective, which means that I get an n right here, so I get n minus 1 down there. So they do see apart free groups. And
David, this 0 should be 1.
pardon?
P not equal.
P not equal 1, yes, thank you. There. Also, please stop me if I write nonsense on the board. This is being broadcasted, so it'll be out there forever. So. Other questions? So why do this? Well, all of this stuff, it originated in geometry actually with a paper by Matthias back in the 70s, and he was studying compact manifolds and covering manifolds, and in this case the group gamma is just a group of deck transformations of this covering manifold. And then they migrated into topology with the work of Kyed and Raum and later with the work of Valvekens. And they also have applications in pure algebra. So a number of these classical ring theoretical conjectures due to Kaplansky are linked to values of L2 Betty numbers, and actually very often the reason why these algebraic conjectures are known for a certain class of groups is because a stronger L2 Betty number conjecture, known as the Matthias conjecture, is known to be true. So they have a lot of applications in various fields, and I think this will end my short advertisement of L2 Betty numbers for groups. And I'd then like to move on to the real topic of the talk, namely quantum groups, and I will again try to give a not too rigorous definition, trying to develop an intuition for them rather and give examples so that you get hands-on examples. So for me, a quantum group will be what is known as a discrete quantum group. So so I'll denote them by gamma, by a black ball gamma, to remind us that this is a generalization of this case up there. So this is not, it's not an object in and of itself, but it's an algebra. So let me put it like this. So a discrete quantum group gamma is a Hofstein algebra. It's actually unital. So what does this mean? It means that I have basically all of the data that I had in a group, but dualized. So it means that it comes with a designated map from C gamma to C gamma tensor C gamma. So maybe over here I will do the case where gamma is actually a group. So over here is just a very simple map, namely it takes a group element and doubles it up. And it has a so-called antipode, which is a poor man's version of inversion in a group. So over here, this is just the linear extension of the one that sends gamma to gamma inverse. And then it has a trivial representation as well. So it has a character to the complex numbers, which over here is just the one that I looked at before. So it is a ring, it's an algebra over the complex numbers, which in many ways behave as if it were the group ring of a discrete group, but there is no discrete group sitting underneath it anymore. It also has a designated state called the Haas state, which over here is just the trace that we used up there, restricted to the group. Right, so the von Neumann trace on the group von Neumann algebra, restricted to the group algebra, corresponds to this so-called Haas state over there. And there are many reasons to study quantum groups. One reason to study quantum groups is because they provide a very natural and nice framework for duality. So for abelian groups, this classical Pontryagin duality tells you that every group has a dual group, and if you dualize twice, you get back. And compact groups have discrete duals, and discrete duals have compact duals, and this all works really, really well for abelian groups, but as soon as you leave that class, you're out of luck. There is no reasonable duality theory, but this extended framework of quantum groups is exactly flexible enough to allow for full duality. Right? So such a discrete quantum group, whatever it is, has a compact quantum group, which is its dual, and you can do everything in a setting of locally compact quantum groups, and it works out really, really well. The problem is, of course, that these things are much, much more complicated to study than groups. There are many reasons for this, but one of the reasons is that they are not, this is going to be vague, they're not really willing to act on spaces. And a very good way of understanding a group is by having it act on some sort of space. These will, in general, be more likely to act on algebras, which are non-commutative analog of spaces, so it's not so weird, but this is nevertheless the case. But what I wanted to see was, how about this? How about these L2 Betty numbers in the quantum group context? And if you look at it, the way I've set it up, you can verbatim copy everything up here, because as soon as I have this Haas state, I can do a GNS space, a GNS space L2 of gamma, which is then by definition the L2 space of this group algebra, quantum group algebra, with respect to this, and the group acts there, and quantum group acts there. And I can talk about derivations because I have all of the ingredients. I have this guy, and I can talk about maps into L2. So there is nothing stopping me from defining HP gamma L2 gamma, which is then just, by definition, the Hochschild cohomology of this guy with coefficients in there with the trivial representation on the right. You can write down the co-cycle relation just as you could for the group. And if the group algebra, the C gamma algebra, is also finitely generated, I can just mimic that little trick up there and embed it into a direct sum of Hilbert space copies. So that works like a charm, but now I'm out of luck. Because in general, there is no need for this H to be a trace. It will be sometimes, sometimes it won't. And if I don't have a trace, this dimension function is a horrible object. Well, you can still do it, right? I can still apply the state, but it's not so clear what I'll get, and calling it a dimension is probably a stretch because it won't be invariant under isomorphism anymore. And if I have a dimension theory where isomorphic copies have different dimensions, then it really shouldn't be called a dimension anymore. But But luckily we are mathematicians and there's a cheap way of getting out of trouble. You just assume your way out of them. Right, so I'm gonna zoom in on the case where H is a trace. This has a name, it's called that the quantum group itself is of Kyed's type. And I will give you some examples to work with. Right now I haven't really defined anything, but I'll be very concrete in a second and write down the objects that I really want to study. So most of you have probably heard of Voronovich's Ornometry 2, and this is a very good example of a non-Kyed's algebra. Right? So those of you who are now thinking of Ornometry 2, it's not going to be part of the talk anymore, because it's ruled out, at least for generic Q, because this H is not a trace, hence this dimension thing does not work out, hence I don't have these BDPs. But if H is a trace, then beta P2 of gamma makes sense. And you can start wondering, what is this number? Okay. It turns out to be difficult to compute. You can prove structural results along the lines of this Chekhov-Gromov result over here, saying that if your quantum group is amenable, whatever this means, there's the definition, then the L2 numbers vanish. Fine, so that takes care of some of them. But for a long, long time, it was wide open to compute anything in this context. So let me tell you about the most natural candidates that you would be interested in computing such invariants for. And here I can actually define stuff properly, I think. So, yeah. So what's the story? The story is about liberated Lie groups, as they are called. So the idea is that you take your favorite Lie group, then you look at the coordinate algebra, and then you forget that it actually is a commutative algebra. So more precisely, there are, let me say, there is this. So the notation might not be very reasonable from this point of view. So there's an n, there's a plus, and there's a hat. And and this might be a little bit, pardon? And an O, yeah. And there's also an O, that's true. But I'll try and explain why all these symbols really ought to be there. But I'm going to just give you, so if this is supposed to be a discrete quantum group, I need to give you an algebra that is its group algebra. So what you do is you take the star algebra generated by n square elements. So this is just like a completely free object. But now I want to mod out with certain relations. I'm going to call the generators Vij, I and j from 1 to n. And I'm going to demand first and foremost that the generators ought to be self-adjoint. Okay, so this is a bunch of relations that I want to divide out. And I also want to divide out the relations coming from V being an orthogonal matrix. So if I write up, so I didn't say this, but V is of course the matrix with entries Vij. So once I take my V matrix, form the adjoint, I do the multiplication, and then I look at all these relations that I get from this matrix being the identity matrix. So it gives me a sum of products. Some of them should be 0, some of them should be 1s. And all these relations I divide out. And this is the algebra of a discrete quantum group that is known as On plus hat. And the On plus hat part is because if you furthermore mod out by commutativity. So if you take this algebra, whatever it is, and furthermore demand that now your variables should commute, then you get exactly the polynomials on On. So this explains the O and the N, and the plus is for liberation, like lack of commutativity. And this is then the group algebra of the dual of this compact quantum Lie group, hence the hat. Okay? So this is an interesting object, and I'll try to justify operator algebraically in a second why people should care about this object, but let me just define the other objects that I want to have, because now that we're at it, might as well define un plus hat, and this is, again, it's given by an algebra, so it's the star algebra generated by, now I'm going to call them uij's, and I'm again going to mod out by certain relations, subject to the matrix with these entrants is supposed to be unitary. So this is the natural condition. So I demand that this is a unitary matrix. Unfortunately, in the non-commutativity case, there is a snag. This is not enough to form a quantum group. I need to demand also that its transpose, whatever it's called, the one where I just star each and every entry, so it's not the transpose, but this matrix, whatever it's called, this is supposed to be a unitary as well. So I mod out by all of the relations coming from this matrix being unitary, all of the relations coming from this matrix being unitary, and this gives me a quantum group, and it's exactly the same story as before. If I impose the commutativity relations, this will be exactly the coordinate algebra of ordinary UN. So this is a non-commutative liberated version of the unitary quantum group. Now, do I want to say something? Maybe you can do, maybe I'm going to go a little bit faster with this guy. So this is supposed to be the same, oh, certainly not the same, Sn plus hat. So what this is done in the same manner with Sn. So I take the symmetric group on n generators, I think of them as permutation matrices, I write down the relation that permutation matrix permutation matrix needs to satisfy, and then I forget that things commute, and then I get a non-commutative version of the symmetric group. So this is like a liberated version of a finite group rather than a compact group, as in the Lie group case. So there are many reasons to study these objects, but if you're an operator algebraist, you might want to study them because they give rise to really interesting operator algebraic objects. So I have, of course, this guy. I have the L2 space, so I have it represented on the L2 space, so I can play the game that we know from the group situation and close it off, say, in the operator algebra topology, the norm topology, and get a C-star algebra. I could also close it off in the strong operator topology and get a von Neumann algebra, and these are then the natural replacements for the group C-star algebra and the group von Neumann algebra. So I get something like C-star reduced of On plus hat, I get L of On plus hat, I get a C-star reduced of UN plus hat, I get an L UN plus hat, and there's a good reason to suspect that these are complicated objects, because in the world of quantum groups, these UN guys play the same universal role as the free groups does for finitely generated groups. So it's if you take a finitely generated group, can subject onto it with a free finitely generated group. This is triviality. And you can do the same thing with bond groups, any one of these Katz type bond groups will be a quotient of the UNs. So these are huge objects in the category of bond groups, very much like the free groups are big objects in the category of groups. So you know quite well that the free groups give rise to really sophisticated operator algebras. In particular, the group von Neumann algebras are notoriously difficult to understand and to tell apart. And it's the same thing here. So there are a number of big open questions. For instance, is L of UN plus isomorphic to L of UM plus for different values of n and m, of course. Nothing is known about this. It's probably very difficult. It's actually, to give you a precise feeling of how pathetic the situation is, it's even open in the case of C-star algebras. So, hint, you cannot use K-theory. Like, if they were free groups, you would say, aha, I'm just going to compute the K-theory, and the K-theory is going to tell them apart. It's not going to be the case. Christian Vogt did compute the K-theory. It does not tell them apart. It does, however, tell them apart from free groups. So these are not free group C-star algebras, but we of course do not know, or I don't know whether this is of course, but these are these L, F, K algebras? I don't know.
Except for n is 2, no?
Exactly. You're setting me exactly up for the next remark. There is a result exactly when n is 2 by Theo Banneker. So Banneker proved that L of UN plus half is actually, L of U2 is actually L of F2. I don't know whether this tells you anything about the higher ones or gives you any sort of intuition. I don't know. I'm not going to make any claims. But in many, many ways, these guys behave as if they were free group factors. So what I mean by that is that if you start measuring various analytic properties of the UN has, they will mimic those of free groups. So this is a 2-1 factor. This has no cartons of algebras. This was proven by Stefaan and Nicolas van der Velde. It is prime, so you can't decompose it into a tensor product of two 2-1 factors. It has the Hoover property, whatever that means. It has rapid decay, whatever that means. This is Brannan and Bernier, respectively. So even if you don't know what all these words mean, these are exactly the taglines that you know will see attached to the free group factors. And up until quite recently, the similar questions were open, completely open also for the ON classes. So, but a couple of months ago, Brannan and Bernier proved that L of ON plus is not a free group factor. So what is known is that if you replace UN plus here, you at least have a negative answer to this question. So they prove that they are so-called strongly one-bounded. And one of the ingredients, this is my sales pitch today, one of the ingredients in that proof is exactly the L2 Betty number computation for ON plus due to Bernier. So he proved back in 2008 that beta 1, 2 of ON plus half is 0. And Collins and Herdel and Thom later proved that beta P2 of ON plus half is also 0 for all other values of P. So I'm not saying much, but what I am saying is that from the L2 number point of view, the ON pluses are significantly different from free groups because free groups at least have a very non-vanishing first L2 number. So now the question is, of course, what can be said about the UN pluses? And this is what I set out to do together with Sven Raum. And the statement is very simple. Getting to your A. So the statement is simply that beta P2 of UN plus hat is 1 when P is equal to 1 and 0 when P is I did it there. So this is the computation. So the thing I did with Sven was in 2016, and we did P different from 2 and 3. Annoyingly enough, we couldn't get the value for P equal 2 and 3. But then Julien Bichon came along, and he has some hardcore homological algebra tools that could also deal with the P equal 2 and 3 case. So we did that together earlier this year. So why is this interesting? Well, it's interesting not necessarily so much because of the value 1. This was actually conjectured already back in 2008 when Venue proved the 0 case of the eta 1 of On plus hat. But the interesting thing is that it does not depend on n. So this is independent on the parameter n. It's just a sequence of ones. So this gives you an analytical aspect of the UN pluses, which differs from that of free groups. All the long list I gave before was consisted of all these properties where the free groups and the UN pluses agree. This is one aspect where they do not agree. And I'm not saying anything concrete about this having an implication to these kind of questions, but it's just a hint that there is certain elements of non-free group behavior present in the UN pluses, which is detectable by analytical methods. Okay, so if I have a theorem A, I should also have a theorem B. Otherwise, I should have just called it theorem. And now you should imagine, now the camera zooms out and there's a little text saying, meanwhile in Los Angeles and Leuven. Because in parallel to this stuff that we did, Stefan and Popar and Sierchenko developed a whole machinery for cohomology theories for tensor categories, including a good definition of L2 Betty numbers as soon as you have a rigid C-star tensor category. Okay? And this definition works well, and you can more easily than in the quantum group case compute it. They're somehow more amenable to computations. And it is probably no big surprise that if such a discrete group has a compact quantum group as dual, this compact quantum group, very much like a classical compact group, has a representation category. A compact quantum group has a representation category. And this representation category will be exactly one of these rigid C-star tensor categories. So in general, if I have one of these objects, so this is discrete, then I have its dual, and this is compact, and then I have the representation category of this guy. But if you look at the surface of things, there's absolutely no reason to expect that the cohomology theory for the quantum group and the cohomology theory for the associated C-star tensor category have anything to do with each other. Because even if you just, instead of computing cohomology with coefficients in L2, if you just take trivial coefficients, sometimes one of the objects will give you zeros, where the other one will not. So even though the two things are very intimately related, their cohomology theories in general seem to be disjoint or orthogonal somehow. However, Stefan's student Matthias Valvekens started computing for these unitary quantum groups the L2 Betty numbers of the representation category. And almost simultaneously with our computation, he came up with exactly the same computation where you just put in rep un here. It's exactly the same L2 Betty numbers. And it turns out that this is actually always the case. So if you measure the dimension, then with respect to the group phenomenon algebras, then the L2 Betty numbers of gamma and the L2 Betty numbers of the representation category of gamma hat, they always agree, as soon as the left-hand side makes sense, right? Because I had this assumption that H needed to be tracial, and then this makes sense. This makes sense in general, actually. But when they're both defined, they agree. So this is so this gives you a more computationally amenable way of getting your hands on all these numbers. So all of the computations that I've talked about, if you combine this result with the original paper about L2 Betty numbers for tensor categories, then you'll get all of these computations for free, so to say. And it also gives you more computations. For instance, the one that I barely defined and that I've now erased, this liberated permutation group, it comes out of these computations of these representation categories that all of the L2 Betty numbers vanish in this case. So this gives you basically all of the computationally relevant open questions for free once you have this. And it's interesting, I think, that these things can be defined purely like within, so without any assumptions on the Haas state being tracial. So this might actually be the correct definition, whereas this, in hindsight, turns out to be an ad hoc definition, which should have been this had I known better 10 years ago. But it's very satisfying that things are coming to an end. So I have talked for exactly 50 minutes. So yeah, I think I'll just stop here.
Any questions or comments for our speaker?
So can you do this L2 Betty numbers and now for the same transfer to the quantum groups or knowledge quantum groups with the L2 Betty numbers?
Yeah, I mean, I can, like, this thing makes sense
Yes.
for the SU.
So have to be calculated?
Yep, you just get a big fat zero.
Okay.
But it's not so weird if you think about it, because these are, they are amenable, or rather the discrete duals are amenable.
Well, not the tensor categories.
Not that that's, but the quantum groups are. So from a philosophical point of view, if you have an amenable quantum group, its L2 Betty numbers ought to be zero. But this is the tensor category and categories are not amenable, which is a little bit surprising actually to me.
What do you know about the possible values of the Betty numbers?
Of what?
Of Betty numbers?
What they can be?
Yes, what they can be.
So you can get 1/2 at least if you look at, so there are, okay, we're getting into more and more exotic examples, but there are these hyper-octahedral quantum groups, and they have first L2 Betty number 1/2, and then there is a class of, what are they called? You know this better. They have this there is the quantum reflection groups, they're called, and there you get all numbers of the form 1 minus 1 over n, where n is a natural number. So the examples we compute are rational.
But of course, it includes all discrete groups, and that, of course, was an open problem for a long while, whether the Betti numbers would always be rational numbers. But there have been counterexamples constructed. So there are countable groups with Betti numbers that are irrational. But these are quite weird and difficult to construct, actually.
And recent. It was open until 2010, where
Yeah.
Tim Austin constructed the first example. And I think it's still open. It's related to this, it's called the Atiyah conjecture, whether these things are rational numbers always. Although Atiyah probably never conjectured it, but he asked the question, more so.
No, it's even, the story is even stranger than that, in the sense that Atiyah writes in his paper, there is no reason to assume that these numbers should always be rational, and they turn into Atiyah conjecture that they would always be rational. It's completely weird how this happened.
But I think it's still open in the torsion-free case. Like, so in the torsion-free case, the Atiyah conjecture is stronger. Namely, are these numbers always integers?
In this counterexample, is it an algebraic number or isolational number, or you don't know?
Like I don't know. There are very concrete lamplighter-like examples, but the first result was not constructed. So Tim Austin proved that there is an uncountable variety of L2 Betti number values. Hence, some of them need to be irrational, right? So, but
now it has been improved in the sense that all constructible numbers, where you define them as the numbers where you can generate the digits one after one by an algorithm, like pi or e, you can realize as a first Betti number.
Okay.
Yeah. And you somehow encode the algorithm, because that's a funny part. You encode the algorithm in the group somehow, yeah? Because that's what you have to do if you...
But we don't have any natural irrational numbers occurring in this context.
So in order to define the L2 Betti numbers, we need some machinery, the machinery that Stefan explained in his course. Right? This requires some effort, right? And so one has to accept to be in a world where representations are not representations, right? Only category of something.
I'm much more comfortable in a world where representations are representations, which I suppose is why it started with this definition and not with the one given by Stefan and co-authors. The question is another question is there an Hopf algebraic definition of L2 Betti numbers without the traciality assumption, and in that case, are they still equal? But as of now, this is just a question with not even an attempt of an answer.
I didn't quite get what the difference between discrete, compact, quantum group, right? So the first examples you gave were discrete, and the ones which have names that look like simple Lie groups,
Right.
are of the discrete kind or the compact kind.
It depends on your point of view. So I try to sell things from a discrete viewpoint because this is where L2 Betti numbers naturally occur. However, these Hopf algebras that I gave you naturally occur as liberations of compact Lie groups. And the point is somehow that you have, so what do you have? You have something like the polynomials on L1, S1, continuous functions, L1 to infinity of S1. So this is a Lie group perspective
Yes.
on the compact group S1, but if you Fourier transform, this is exactly the same as this picture. So you can move back and forth. You can think of it's actually it's more natural, I suppose, to think of these. Where did they go? So the C of O n plus hat as a polynomial algebra on this deformed Lie group, but it depends on whether your brain looks at it before or after Fourier transforming, basically. I don't know whether that was an answer.
Anyone else? Let's thank the speaker again.